Hello? Yeah, can you hear me, Jagadeesh?
Yes, sir. Yes.
Okay, fine. So then Sivakumar is done masters from this pharmacy and did PhD from IIT Madras in biotechnology. And he has vast experience in, he was in Italy and JSPS fellowship from Japan, and now he is a Marie Curie fellowship holder. Now he is in Turkey in Sabancı University. So he has vast experience in the biotechnology field. So let's everyone give the project details, then we can give the comments.
Hello, sir. Okay. Sir. Welcome. So we have some 12 students working on space food project. I'll connect you with the 12 students. 10 students are doing MSc first year in food technology, nutrition and foods and dietetics. Then one student, she's a working professional from Ramachandra University. Then one student from IIT Madras. So I'll connect.
Okay. So 10 students from MSc in IIT Madras.
No, SDNB, Vaishnav.
Oh, Vaishnav. Okay. Yeah, great. Yeah, let's join.
Yes. So today we have a weekly mentor meet with our IIT interns. So there are around 20 students who are doing research on various topics. And for most of them are still in quarantine inside IIT Madras hostel.
Yeah.
Not able to come out. So we created this idea of online meeting. Who is the first one to start? Kiran. Okay. Kiran Patel. Okay. Kiran Patel, you can start. Give a brief 10 to 20 second intro to Shivakumar sir as well.
Okay. My screen is visible, right?
You need to reshare your screen. It's loading. Then you can start.
Yeah. Just let me know if the slide doesn't shift. Okay. Yeah. So first of all, we'll just briefly talk about what a missile is. So a missile is basically a weapon which is designed to deliver a payload. So it can be explosive. It can be.
Can you be a bit louder?
Yeah, sure. Just a second. Is it better now?
Yeah,
yes. So basically a missile is a weapon which delivers a payload, and it can be explosive or it can be a biochemical weapon. Now the objective of a missile is to deliver it with high accuracy and great speed. So on a broad basis, we can say there are two types of missiles. One is a ballistic missile, which is powered by rockets, and there are multiple stages of rocket, and it follows a trajectory which goes upward and then it descends onto the target. So it can carry any type of weapon as well. There are 4 general classifications of such a missile, which are short range, medium range, intermediate, or long range, which are ICBMs. The other type of missile which we can classify is a cruise missile. So a cruise missile is capable of flying at low altitudes, and this is why it is difficult to detect than a ballistic missile. A cruise missile is powered by jet engines similar to an airplane, and it is self-guided and uses multiple methods to accurately deliver its payload. It even uses terrain mapping, GPS, and inertial guidance, since it is very near.
Just one clarification, Kirtan Patel. Actually, you are in BTech which year?
3rd year.
Aerospace.
Yes. Yes, sir.
Okay, these missiles everybody knows. So what is your focus of work? Something like that. So your objective. So it's general things everybody knows it.
Okay, then I think I'll move directly. I was giving a brief introduction. I'll move to the next second part of it,
Yeah.
which focuses on what I've done. So my focus will be basically on two things, which I've narrowed down. So the first is stealth technology. So I think everyone knows what stealth technology is. So in November 2021, the Indian Navy has introduced a stealth guided missile destroyer, which is INS Vishakhapatnam, and it carries anti-submarine missiles, and it was commissioned recently. So it was a 35,000 crore project, and there were a total of 4 warships which are to be delivered. The first one was delivered in November 2021. 2 will be delivered in 2023, and 1 will be delivered in 2025. Now, the thing is that the stealth technology which India has used is limited to ships. On the other hand, the AGM 158 that has been in service with the US Air Force since 2009 is a stealth technology missile, and that is what they have been using since 2009. It has been developed by Lockheed Martin. It carries 450 kgs of armor, and it carries it to a distance of 1,000 kilometers. Now, not only US, but it has even extended the missile to foreign services, like it is being used in Australia, Finland, and Poland since 2014. India has not been able to develop such a missile, and the stealth technology is limited only to ships up till now. So this is the point which I'll be focusing on further. It has already had 2,000 such missiles, which were given to the US Air Force in 2016, while India has none of such missiles. The other part which I would like to focus on is the electronic warfare part of it. Yes. So electronic warfare, it is basically using electromagnetic spectrum to interfere with the enemy's communication system. So we can broadly classify it into 3 types. First is electronic attack, in which we use electromagnetic waves to assault enemy air force electronic infrastructure, and to save ourselves from such attack, we have electronic protection, in which if the enemy poses such an attack, we should be able to defend our own systems against these attacks. Now, this can be done using multispectral radio frequency or infrared, and we need to detect if such a frequency is used around the equipment which we use. The third is the electronic support, in which if we have some data which needs to be transferred, we should be able to transmit it in such a way that it is not intercepted or tracked by enemy electronic systems. So these are the 2 topics which I found to be interesting, both in which India lacks a lot from its enemy counterparts. Now, India has a joint electronic warfare system between developed by DRDO and the Indian Navy, and it has 5 different types of indigenous EV systems. For the Navy Sangraha, the another electronic warfare system which is developed by the DRDO and the Indian Army is the Samyukta, which has been used till now, but all of these are limited to ground vehicles. These are deployed on the ground, and these are carried out in a 100-kilometer range at max. So on the other hand, the US Air Force in 2015, they had a CHAMP payload, which is a counter electronics high power microwave advanced missile project. In this, what they do is they launch the missile, and the missile sends out a high frequency microwave energy, which non-kinetically destroys the enemy electronics. So that is something which has not been found in the Indian Air Force artillery, and that is something I would like to conduct the further study on in this internship. Further, the next part which I had to cover this time was the different agencies which India uses to develop and manufacture its defense technology.
Kirtan Patel, it is fine. So then, so you have given some broad what is happening and what is going to happen. So technically, what it's like, I need some technical specifications. It's like if you are developing stealth technology, there is several kind of stealth technologies. It's like ultimately it is like the radar signal which is transmitted from the it should not be detected by any radar signal. It is something like the stealth technology which was earlier used. Now it is like dispersing of radar signals by using some specialized materials. I think even Ashwini also knows that. We have Ashwini. She's not there actually. So we have done something.
It's I am here only.
Yeah, you can also tell him. So what we have, what we are doing, so that he can grab something from the what we have proposed.
Yes, sir. Actually, we have tried to incorporate composite itself in the nose cone part, so that the radar frequencies would be observed by incorporating some the ceramic materials. This is the idea we have consolidated in our previous research.
It is some materials are like dispersing or absorbing the radar signal. So it is like if our missiles or our fighter aircrafts are going to enemy territory, so our objective should not be detected by the enemy's radar signals, something like that. So it is like to confuse the enemy's detection, something like that. So that is the so far we have seen. But other than that, you can also send. It's like stealth means it is like hiding our object from our enemy's detection point of view. It's something like that. So or else, yeah. So you have to see in that case. It is like in terms of geometric point of view or material point of view. So how to evade like enemy's detection signals. So that is one thing. So for that, you have to do a lot of literature survey. What is the current status and each and every, because in many of the countries, this kind of stealth technologies are not known to public.
Right.
It's limited. Okay.
Right.
So with the available data, so what they are doing, so sometimes it is like some 2 years back or 3 years back, what they have done. Now only it is it's something public to, it is released to public, something like that. It is happening.
Yes.
So you have to find out what technically you can update, what is the current technology and what you can update, something like that in the stealth technology. In the electronic warfare, I'm not much aware of that. So electronic warfare means it is again the signal what is like, it's like interfere the signals and like decoding of some you have to develop some algorithms, something like that. I am not much aware of that. So a lot of data are available, so you can yeah, you can you have to do some fundamental research. What so far it was done, so what is the current status and what you can go first, like advancement or something like that into next step. So that you have to do. Okay.
Okay. Yes, sir.
Okay, so you have to search some recent literature, some journal papers, and based on that you can carry on. So both the topics are good. So whichever you are feeling very good, so you can go ahead in that direction. Okay.
Okay, sir. Thank you, sir.
Okay, Kirtan. So then we can move on next. Jagadeesh, who's the next?
Next will be Pavitra, sir.
Yes.
Yeah, Pavitra, you can start your screen sharing.
Hello, sir. Yeah, I'll start sharing. Is it visible, sir?
Yes, yes.
Sir, actually, I didn't attend the previous thing. So briefly, I'll just touch upon to just like come to the actual like part which I did. The main part is like guided missiles. That is what we are looking into. And these guided missiles, when I started the research with, I wanted to trace back where it started from. So I did it in two ways. One thing is like from the ancient manuscripts, and the other thing is like actually what the proofs which we have for that. That is like the Tipu Sultan things and all, Tipu Sultan Mysore rockets. For that, we have like physical proofs in found in Bangalore and all, where they have the casings and all found over there, and that was like the early start on point. So
Pavitra,
like
I
they
think
had like
because
certain,
even sorry for interruption to you. So then it is like histories we don't want. So what is the current status? So what you are going to do, something like that? You
yes,
just,
so in this actually they have like some knives and all attached to it, so that when it launches, it like splits into multiple multiple different okay, 1 second, sir. So when I looked into like a few of the ancient manuscripts, the Brahmastra and all has like this atomic weapons kind of component. So each one of it has some different kind of technique which can be actually related to the current scenario, and can be connected to the current environment. The Sudarshana Chakra is actually like the motion detecting weapon, which actually like attacks a particular person, and like it's like a selective destroying kind of thing. So these are features which actually is being used in current warfare as well. But there are some features which were described in manuscripts, but we aren't able to trace back exactly what they are trying to mean it. So there is one description that in Brahmastra, the head of it looks like the Brahma's face and all. So this can be actually the point of like the nose part of the missile can actually be described like that. So there are a few things like that. There is this Sabda Veda Astra, which is like basically based on the audio, wherever the audio deduction, it goes and attacks using that. So these techniques can actually be incorporated with the current missiles as well. So, and the Agni Astra, Varun Astra and all, like they have like enormous amount of flames and water is produced. So even if in naval the ship war is happening during that time, even the water is present around, some kind of inextinguishable material which is actually used to attack can actually be seen. Like the point is like connecting to the current technological advancements which we have and trying to relate with it. And like as the previous person also told, like a vehicle disappear, there is this salva vehicle disappear, which is actually not like, it's not disappearing, it's just like in the range of deduction, it's not getting deducted. So how to manipulate the enemy troops radar deduction is also a part of it. So this is how it started for me. And 1 second, sir. Yeah, so we have like Indian missiles, which is of different ranges and all.
Pavitra,
but-
you can skip all these things.
Okay.
So what you are planning to do, so it is like Brahmas, it's fine. So then,
Okay,
so
sir.
I need some technical strong base. So what you have done some literature survey. So, and because you are aerospace, you are from aerospace, no?
No, so mechanical engineering.
That's fine. So then it is like, okay, so ballistic missiles and
So
ancient manuscripts.
basically this hypersonic missiles, which is actually like Mach number greater than 5, the idea for it, I got it from Vaishnava Astra, which actually travels with fast speed and all, the hypersonic part of it. So basically it's even the defense minister has mentioned that this is the focus point right now, where we have to develop something in hypersonic area. So that is going to be my central point. And for hypersonic, basically this is going to be like a cruise missile type, wherein like it passes a particular trajectory path, and then based on the navigation, it follows after a certain path. So that is my plan. So for that, like mainly I want to focus on the design part of it, the propulsion system of it, because as the speed is going to increase, the friction, heat generated and all will also come as a like disadvantage for us. So the using metallurgy and design, like looking into like solving these problems, and like the computing system also needs to be like made more proper. So that is what like my focus, like what I want to do.
So design of propulsion systems means you have to go for the scramjet, the supersonic combustion ramjet engine. So there is several issues there. Do you know what is meant by positive thrust or negative thrust?
No, sir. No, sir.
No, positive thrust means your drag should be less than, so your thrust, whatever the thrust you are producing should be more than your drag. Then only any vehicle could go forward. Okay, some net thrust should be positive. Okay. It's something like that. Then metallurgical point of view, I think you are from mechanical, so you can do a lot of heat transfer analysis like
yes, sir. Yes. I like found a research paper based on it.
It's like metallurgy means you can, it's like molybdenum alloys or some inconel alloys, so that you can have, it can withstand very high temperatures, and you can use some Bart's equation. It is like the Bart's equation is exactly used for like from high speed flow, let's say Mach number more than 5. So from Mach number 5, so how the heat is transferred from gas to solid. Okay, there is in between boundary layers like velocity, momentum boundary layers, and thermal boundary layers. All are in that. It's based on mostly Reynolds number, Stanton number, and Prandtl number. So all these things. So it is like you have shown some broaden area. So you have to be specific, like whether you are going to develop some scramjet propulsion systems or like heat transfer or some materials. It can withstand very high temperatures, and we have to, obviously we have to provide some cooling. Otherwise so far the material which is available in the earth, which is not withstand more than 1500 degrees centigrade or something like that. Even in gas turbine bed also we are using some inconel alloys, but still we are using some film cooling and some kind of cooling methods. Then only the materials can withstand. Because in terms of scramjet propulsion systems, it is like even the flight speed itself more than Mach number 5, no, 5 to 6. So in that case, the energy which is entered into the propulsion system itself around the temperature is around 1000 degrees centigrade, and the available with the available fuel, like even kerosene or whatever it may be the fuel, it's like it can produce only 2500 degrees centigrade. So it is like 1000 to 2500 means it's only 1500 degrees centigrade delta we are getting. So with the delta, it's like always the temperature, the delta is the one which controls the thrust. It is like m dot Cp delta, you know. So it is like, so that much thrust only we can produce from the propulsion system. So any kind of scramjet propulsion system. So that is the major limitations. It's like disadvantage for not getting a positive thrust. Okay, so I'm just giving some simple idea. So what is the current issues? So either we have to go for some fuels or like very high calorific value fuels, or we have to reduce the inlet temperature, something like that we have to see. Okay, so
sir, is there a possibility to have some sort of like hollow casing with some coolant material inside it, which reacts with the like resistance provided by the oxygen, and like it provides like multiplies the cooling amount or something? Like, is that a way? Like,
no, I didn't understand. So you are just confusing me. So it is always we are using some counterflow cooling. It is like fuels. If you see in liquid rocket engine in the convergent divergent section, we are supplying the fuel from the divergent section. So before it enters into the combustion chamber, the nozzle valve materials are getting cooled by the fuel as coolant. So it's something like that. So you just show me the concept. So whether it could be possible or not, I will tell you. Okay.
Okay, sir.
So in terms of G forces and vibration and humidity, I don't know what we can improve. So in terms of vibration, it is based on the material. So you have to use some kind of stiffeners to reduce the vibration. So whenever we are dealing with very high speed vehicles, so always we have to do the structural dynamics design. That is very, very important.
Okay.
Because we don't know what is the natural frequency of the particular material and what is the frequency which is developed from the combustion sources and the external aerodynamics. So this is, it should be very, very particular. So if you know, some resonance could happen. No? So if this natural frequency as well as these forced frequencies are coincide, so the vehicle could collapse.
Okay, sir.
So these are all the things. So you just to be specific. So which you are going to do. So I will.
So basically, the metallurgy and design aspect is what I'm like focused towards.
Metallurgy means, yeah, you can try for like different materials which can withstand very high temperatures and thermal and pressure loads. It is like even carbon.
Design of specific part can be concentrated, no sir.
What?
Instead of design of specific part for the
Yeah,
missile.
something like that. So then, because that is like, if you see the combustion chamber, it can produce the 2500 degrees centigrade, and you have to do the heat transfer analysis. Okay, so from 2500 degrees centigrade, so much Mach number. So how much heat is transferred from the hot gas to the wall, nozzle, the combustion chamber wall or nozzle wall. So to withstand that much heat load, what could be the material? It's like you can see like carbon composites or yeah, some molybdenum alloys, something like that. So sometimes it can withstand that much temperature, and it should what I can say, it should some ablative heating, cooling also sometimes happens, so that erosion could happen because of that very high speed. That also you should be very careful.
Okay, sir.
So these are all the issues. So you just pick up some particular concept, like if it is metallurgy and design means, yeah, obviously the how much heat is transferred and which material can withstand that much temperature. So you can improve upon it. Okay.
Okay, sir.
Okay, Pavitra. So then, is there anything else?
That's it for now.
There is one. There are some around 20 students. They are getting trained and building solid propellant rockets, and we are also teaching some applications, how to test it, and we are teaching them using horizontal launch. If you are in campus, you can drop in to research part. So that happens next week. I'll ask Pvt to connect with you.
Okay, so right now I'm not in campus. I'll be
Okay.
coming for January 4th. I'll be coming to Chennai. Sir.
Anyway, so Pvt will update you. So during that time.
Jagadeesh, you can share the video to her so that
Yes.
just seeing or sharing video, it's the same.
But hands-on up, and it's like to build it hands-on. So that.
Anyways, we will come on
Yes,
next week.
Yes. So once you reach back, you just get in touch with me.
Okay, sir. Thank you.
Okay, so then, Jagadeesh, is anybody from biotechnology? Because
Malyapan sir is waiting. So
yeah, because Sivakumar is like
got it.
so he's because of him only I just postponed this meeting today.
Got it.
So because he has some other work, so
7 o'clock the students are going line. The space food students.
That's fine. So then I don't have any problem, but Sivakumar has some other work because he has writing some papers. So we should finish.
I'll check and update you.
So who is the biotechnology student? So let's finish them. So then,
yes. We check an update. So in the order, next is Abhinav.
So meanwhile, can I just go ahead and present my screen? If it's okay.
Okay.
Yeah.
Okay, I'll do that. Yeah, so I was able to attend the meeting last time, but I wasn't able to present because I was sick the whole week. So basically, my topic is also amphibious missiles, and so these are basic definition. These are basic theory about amphibious missiles that I wrote down. But since we see that here the missiles have 5 system components: targeting, guidance systems, flight system, engine, and warhead. My main focus and my interest was towards the guidance system, as in how the missile goes and hits the target perfectly in almost all cases. So I kind of went through what type of guidance systems are there and what are the other all the guidance methods which are there. And towards the end of my very basic research on the guidance system that India has currently, and the ones that it is buying from other countries and importing from other countries, my plan going forward is to solve the problem of basically precision killing. So there are two issues. First is when the missiles don't clearly hit the target on point, and the other issues is basically the enemy kind of recognizing the missile in the range and then trying to combat it. So with this, I found that the loitering munition system is one of the things which can help solving both of these problems. And in a very recent news, I also read that the Indian Army plans to buy medium range precision kill systems, which has this loitering munitions. Now loitering munitions is something which is it basically loiters over the target for some time, so that even a target which is kind of hidden and appears only for a few seconds can get hit. So I wanted to kind of focus on this. I wanted to see what I can do here, and there is a clear research gap in India currently because we don't have a loitering munition system of our own, and we are currently looking to import it from outside. So so basically, yeah. So it basically allows selective targeting and of any target which are looking at. So I wanted to focus on this. At this point I don't have a particular base on how to get started on this. I've just been kind of doing some kind of research of what India has currently and what it is lacking in. Not being able to build a base, but so would love all sort of help from you to take this forward.
It is fine. So do you know what is the response time of any munition systems, or like what is meant by loitering? It is like it is just to disperse, or what is it actually?
So sir, basically in loitering munition system, what happens is the missile itself recognizes the target while it's in air. So it's a mix between the cruise missiles and then unmanned combat aerial vehicles. So it's not exactly a cruise missile because it loiters for a bit more in the air, and while it's loitering in the air, it kind of chooses its targets and then goes and hits it. So it stays in the air a bit longer, then chooses a specific target and then goes and hits it.
That's okay. So then that means the response time of like let's say if any munition systems, it's like if you just press the button, so it will take some time to hit it. So that is like a response time, or we can say it is like a gap between the it's like it's ignition gap or something like that we are telling. Because it is like in airborne vehicles, it is always in very high speed. Okay.
Right.
Even if you see Brahmas, any kind of missiles, it is it can it flies around some Mach number 2 or 3, something like that. It's something like that, no?
Oh, so not sure myself.
It is something like that. So,
okay.
So in that case, we need some quick response munition system. So that is for that you have to see different kind of propellants or munitions are available. So which can be used for the particular your area of research that you should first select.
Okay.
So then, so I need some table like if you are using this kind of propellant like ammonium perchlorate or sodium nitrate or some carbon, and a lot of things are available. So you have to see which is giving quick response to your application. So based on that, you can choose it.
Okay, sir. So I'll start building my base from this, and then we'll see you in the next one.
So precision guiding is like again, it is based on several factors. So first you have to see these things, so then you can carry forward.
Okay, sir. Got it.
Okay. So thanks Abhinav. So
Thank you very much. Sir.
Puvi, so then thanks. So then Puvi, so you please check who is from biotechnology.
That's
So that
Pavani,
so
sir.
then-
Pavani. We'll coordinate with. I'll get Malliyappan sir's number from you, sir. So we'll coordinate separate timing with all the 12 students with Shivkumar, sir. Will that work, sir? Hello.
Yes, Jagadeesh.
Yeah. So we'll connect with Shivkumar sir separately and have a meeting with all the 12 students who work on space foods. Pavani not picking, not
So
today.
Is there available now?
Yeah. She is not picking the call. That's what Puvi told me.
No, is there anybody from now biotechnology students?
Puvi, where are you?
No, sir.
Only Pavani.
Yeah, from IIT, she is the one.
We
So
will
the
connect
time
with.
slot will be after
So, what's the
Yeah.
time slot?
after 4:50, bro.
4:50.
After?
After 4:30, she will come.
What about the other students, the biotechnology students, as you mentioned?
They have exams, so they are in
Okay.
separate groups, sir. They are not in part of this group.
So
that's the schedule for next week, sir. Okay. For biotechnology, separate space foods, we segregated them together. Update Tania. That I'll connect, sir. I'll connect with you.
okay, so then Sivakumar, it's up to you. So then if you continue, if you want to continue, or it's up to you. So sorry for
It's
that.
okay. It's okay, Jayaraman. Actually, I have some other work, so I have to leave now.
I'll
So
Okay.
I
get
will
your
join
number,
you.
sir.
I will join whenever the biotech students join
Yes.
for the meeting.
I
It's
think
okay.
today
Thank you very
was,
much.
yeah, thanks, Sivakumar. So
Oh,
sorry for
sorry.
that.
Yeah, it's
So,
okay. No problem. Yes.
so today it will not be there, no? So
Today it won't be there.
Jagdeep?
Today it won't be there. Inniki irukadhu.
Okay, no problem. Okay.
So I'll connect
It's okay.
with
Whenever
you,
they
sir.
are ready, whenever
Yes.
they are ready, we can have a meet. It's okay. No problem.
Okay.
Because we
Thank you.
suddenly got a huge group of students specifically working on
Yeah.
space foods. So I put them all
It's
in a
okay.
separate thing.
It's okay. No
itself, yeah.
problem. Yeah. Great. Thanks, Jayaraman. Thanks.
Yes,
Okay,
I'll
okay,
collect your
thanks.
number from there. Thank
Yeah.
you. Thanks for that.
Please.
Yeah.
Yeah. Thank you.
Okay.
So next in the list, it's Aditya.
Next will be Ujjwal.
Ujwala. Okay, Ujwala.
Yeah, Ujjwal.
Okay.
Yeah, am I audible?
Yeah.
Yes.
We'll carry on.
Yeah, so in the last meet, I presented the general overview on amphibious missiles, and you specifically instructed me to work on fuels part. Actually, the two main important things is the guidance system, control system, and the fuel part. So currently, I did some research on the fuel part. So basically, in fuel part, in the last meet only, I came to the conclusion that at least in the initial stages of launching the amphibious missile, we need to use solid fuels. And here is some justification why I feel that solid fuels are important. So first thing is simplicity of the solid fuels. They are very easy to maintain and they're easy to design also. All you need to do is make the solid fuel paste and just put it in a tube, in a rocket tube, and then obviously line the tube with insulation, make sure the material can sustain high temperatures, and that is pretty much it. Even the manufacturing costs are very easy. If you look at liquid fuels, you need so many pipes, pumps, storage of the liquids, make sure the liquids don't leak out from the chambers, etc. And so, yeah, solid fuels easily outperform liquid fuels in this area, and even they have a high thrust to cost ratio. If you look at the materials used for solid fuels, it's ammonium perchlorate, aluminium, whatever the materials are. If you sum up all their costs and if you find out how much thrust they generate, it has a high thrust to cost ratio. So it's very affordable. And then storage stability. Solid fuels are also very easy to store. They can be stored as long as 30 years once the rocket is manufactured. So once, like, let's say India is keeping some missiles in its inventory, it need not continuously, keep them under surveillance. It also has resistance to unintended detonation. For example, you must have seen when rockets launch like SpaceX, etc., sometimes detonate. There is some margin of error. But for solid fuels, it's hard for accidents to occur. So if the solid fuel chamber, etc., is manufactured properly, then there is very less chance of deflagration, which yeah. So it also generates high mass flow rate out of the rocket if you compare it with liquid fuels. So therefore, it produces greater thrust. But there is one caveat to this, which I'll explain in the next slide. So yeah, and in fact, due to all these advantages, almost all modern day rockets, even amphibious missiles, SLBMs, they use solid propellant boosters for the initial launch. So also with these advantages, there do come some challenges or disadvantages that we need to deal with. The one disadvantage or difficulty is controlling the thrust. For example, if you have a liquid fueled missile, you can control the mass flow rates of the fuel and the oxidizer, and by that you can control the final exit nozzle mass flow rate. But for solid fuels, once it's ignited, right, you cannot stop it. It just continues. The reaction continues. So liquid fuels you can control, but in solid fuels you can't control. So therefore, there is no active thrust control. So you cannot. So once you ignite the solid fuel chamber, it will run its course and it cannot be stopped. So another difficulty of using solid propellant is that they have very low ISP. So what is ISP? It's called specific impulse. Conceptually, it is basically the thrust of the rocket divided by the weight flow rate of the fuel. But you can just use this formula, exit speed divided by G. So basically, the velocity of exit for the solid propelled rockets, that will be less compared to the exit velocity of liquid fueled rockets. So here is the fact: best performing fuels have high specific impulses, and that is hydrogen as fuel and oxygen as the oxidizer. That's why NASA always uses this hydrogen-oxygen combo for its rockets, at least in the highest stages. So here is one table where I calculated the specific impulses for various fuels. Solid fuel has 260 seconds. Hydrogen, oxygen released into vacuum, that is in space. If this is detonated, then it'll be 450 seconds. At sea level, if you use this fuel, it'll be 370 seconds. So yeah, you can notice that. But there is a way we can overcome this, which I'll be explaining. So yeah, so now let us explain the constituents of the solid rocket motor. Solid rocket motor is basically the entire engine which has the solid fuel. So basically, this has a combustion chamber, which is basically where the solid fuel is housed. And it has the exit port, a nozzle basically, and the igniter, which ignites the solid fuel, and then the propellant. The propellant is the main thing that we need to develop, because exit port and all, they've already been engineered. So the propellant, now let's come to the constituents of the propellant. So basically, this propellant has an oxidizer embedded in a fuel. This is the main reason why I chose a solid fuel instead of a liquid fuel, because when you have a propellant which has its own supply of oxygen, you don't need oxygen from air, which is the exact reason why this missile can be detonated even underwater where there is no oxygen. So if you keep the solid fuel inside water and if you ignite it, the reaction will still happen and the thrust will still be generated. When you compare it to ramjet engines, you need a steady flow of atmospheric oxygen for the engine to work. So now if you want to look at the percentage composition of the solid fuel, it consists of aluminum powder, ammonium perchlorate, and binders. So what is aluminum powder? This is the metal which absorbs or which takes away the oxygen from ammonium perchlorate. Ammonium perchlorate is the oxidizer. A binder, as the name suggests, binds this aluminum powder and ammonium perchlorate together to create a homogeneous mixture. So this might remind you of thermite reaction, where aluminum reacts with iron oxide, where the aluminum removes the oxygen from iron, generating heat. It's very similar to that. This is a rough composition, 16, 17, 14%. But if you want to look at the detailed breakdown, this is the polymer, this is the binder. There's some also catalysts, antioxidants, extra stuff. But this is the main composition: aluminum powder 16%, ammonium perchlorate 70%, and binders 14%. So now let us look into what are the various types of oxidizers that we can use. So in olden days, or not that old also, like before I think 2000s, in the 20th century, potassium perchlorate or potassium nitrate was used as an oxidizer instead of ammonium perchlorate. But the scientists or those people, they switched to ammonium perchlorate. Actually, ammonium perchlorate, I'll just refer to it as AP, just like how rocket industry also uses that. So the reason why they switched to ammonium perchlorate instead of potassium perchlorate is because when ammonium perchlorate combusts, it produces completely gaseous products. For example, if you combust potassium perchlorate, you'll get some oxides of potassium and they're solid particles, and that might interrupt the the flow rate, meaning you won't like you have solid particles and you have gases, and that isn't easy to handle. So ammonium perchlorate produces completely gaseous products, and those gaseous products involve oxides of nitrogen, which, if you know, that is dangerous, which is why I'll come to green solid fuels also later. There's another oxidizer called ammonium nitrate, which is an alternative to ammonium perchlorate, but it is less energetic, it is less efficient, and it also has a slower burn rate. So what scientists did is they mixed AP and AN and ADN to produce higher ISP and lower HCl production. ISP is that specific impulse. The lower HCl production. If you notice ammonium perchlorate, it has chlorine in it. ClO4 is the ion there. Ammonium ClO4, and ClO4 when it combusts, it produces HCl. Now HCl is very dangerous for the atmosphere, which is kind of obvious. And the reason why this happens is, first of all, it's bad for the ozone layer. If you have chlorine ions in ozone layer, that will deplete the ozone layer, which is very dangerous. And the HCl isn't a good gas, because if it mixes with atmospheric precipitation, it will result in acid rain, which is also bad. So actually, I'll come to some alternatives to this in the next slide. And here's some convention. The propellant packages are referred to as grain. So if you look at propellant and the combustion chamber, propellant and the storage is called grain. And so now we covered oxidizers. Now let us come to binding agent. Binding agent is the agent which binds the oxidizer and the metal powder together. And there's nothing conceptual in it. They're just standard chemicals: polybutadiene, acrylic acid, EVA. So these are the industry used binders. None of them are really toxic. I mean, there's a lot of concept in oxidizers, but I think there's not much. We can use any one of them. We can do some experiments and find out which suits our rocket. Here is some data regarding their density. We can do some optimization which has lesser mass, etc. So from the above lines, the qualitative constitution of solid propellants is understood. And also in the beginning, we said solid propellant rocket motor is hard to control, because if you look at something called thrust vectoring, it is what is used in SpaceX, NASA. Basically, the nozzle can change its orientation to balance the entire rocket's mass. But this is hard to do for solid rockets, because first of all, in solid rockets, you cannot control mass flow rate and you cannot even change the orientation of the nozzle. But there is some engineering trick that we can do. What we can do is we can make this less chaotic by introducing stages to the rocket in the solid propellant. Basically, we'll split the solid propellant chamber into multiple chambers, sub-chambers. So basically, it's partitioned into multiple sections, and each section can be ignited on command. Because once a section is ignited, you cannot stop it. So why not just split it up into multiple sections where you can control each section? And such an arrangement is called a pulsed rocket motor, which we can use if you want to control it. So now we can go to green propellants, because as I mentioned before, ammonium perchlorate is actually very widely used oxidizer. But recently, even DRDO also, all scientists realize that it's not good for the environment. So that's why scientists are aggressively developing green propellants. So basically, ammonium perchlorate as an oxidizer releases HCl as a combustion product, and this is dangerous for environment. It can degrade ozone layer, cause acid rain, etc. So to mitigate this, green propellants are researched by various organizations across the globe. So now we can actually look into ISRO, which is actually an Indian thing. So it's actually developing green propellants. So what ISRO did is it was making eco-friendly propellants by using these chemicals, glycidyl azide polymer, whatever this is. So they tested it at a laboratory level, meaning they didn't build a proper rocket and put it. But maybe we can do some experiments on this, maybe some simulations, see whether this is good. So what ISRO did is, instead of using ammonium perchlorate, it used GAP and ADN as the oxidizer. And at a laboratory level, meaning it's research only, it's not practical. We don't know if it's practical or not. We should do our own tests. So what they said is, if you use ADN and GAP instead of ammonium perchlorate, it will eliminate the emission of chlorinated exhaust products like HCl, etc., which which are dangerous, as we know. So this is a good alternative that we may research. Also, ISRO is also carrying out various green propellant combinations, such as hydrogen peroxide as an oxidizer, liquid methane, ADN, methanol water, all those things. So yeah, but this is like very advanced research. I don't know if it's used in industry, but in industry, ammonium perchlorate is used. Yeah. Yeah, and one more thing, as I said, it's bad for the environment, right? If you use ammonium perchlorate, it emits chlorine. But one good thing is, by chance, solid fuels are only used in initial stages of the rocket, because in initial stages you don't need much control, right? Because like, what is the disadvantage of solid fuels? The only disadvantage is, the main disadvantage is, you cannot control the fuel. So why not just use it in the initial stage, and once the rocket attains the necessary speed and necessary height, then you use ramjet or scramjet or anything where you can control the rocket. So, and as you know, at initial stages, let us say HCl is produced, it cannot reach the ozone layer, right? Obviously, it will be harmful near the ground, but at sea level, if there are chlorine ions, it won't really go to the ozone layer and cause acid rain and all, right? If we can contain it. So that is why it's not really that terrible thing to use solid fuels with ammonium perchlorate as oxidizer at sea level, because even though chlorine is produced, HCl is produced, it will stay at the ground only if we do a good cleaning up job there. So yeah, so we can do this. This is one nice thing, but yeah, still we can develop high energy materials which are economically sustainable and environmentally friendly. So yeah, so what is my plan, since I've researched solid fuels? So obviously, I don't think using solid fuels for the entire journey of the missile, that is from the launch till it hits the target, I don't think solid fuels will do the job, because as I said, solid fuels are hard to control, meaning if you want to, let's say, change the rocket's velocity by this much amount within this period of time to hit the correct target, you can't do it, because solid fuels are hard to control. So what I was thinking is, we'll use solid fuels at the initial stage of the rocket, that is the boosting stage, and then when the rocket reaches a sufficient height where there is air, where there is atmospheric oxygen, where there is not much need to use an oxidizer, we will use an engine which takes advantage of atmospheric oxygen, that is ramjet scramjet. But ramjet scramjet won't work in underwater. So for underwater, we will use solid fuels, which has its own oxygen, and then when it reaches the atmosphere with sufficient velocity, then we can use scramjet or ramjet to hit the target. Actually, this is what SLBMs and ICBMs do. So yeah, SLBM is submarine launched ballistic missile, which is basically amphibious missile only. So basically, what I propose is, SLBM can be launched in such a way that the solid propellant is used for the first few initial stages, where it can be underwater as well, and after that, liquid propellant can be used for the air medium if it's a long range missile. ICBMs is intercontinental ballistic missile, meaning it has a very monstrous range, like 10,000 kilometers. It is intercontinental, as the name suggests. So basically, it has three phases: boost on initial launch phase, where I propose we will use solid fuels, and the mid-course phase where we will use liquid fuels, and the terminal phase where the missile hits the target. And if the target is on the surface, then perfectly fine. So now what I propose is, yes, when the missile is launched underwater, we can use solid propellants to gain velocity, reach the atmosphere. And once there is that sufficient velocity and sufficient airflow rate through the engine, we will use ramjet or scramjet. Yeah. So maybe I think if it's offline, maybe we can experiment with some solid fuels and see how well they work.
Yes.
Yeah, Ujjwal, it is like solid propellant. Yeah, you have done some research on that. So the thing is, like, so far we are using this HTBB, CTBB as a polymer, and ammonium perchlorate as a oxidizer, and aluminum as a fuel again. So these things are like, it is compatible with one another. So that's why we are using it. Otherwise, these potassium nitrate or other polybutadienes, all these things are not very compatible, because it is polybutadiene. HTBB is a polybutadiene, it's a rubber. So the rubber has to be embedded with this ammonium perchlorate kind of oxidizers, and even it produces so much amount of HCl. We are using it because there is no other alternative so far. But whatever you are proposing, it's like ammonium dinitramide and GAP, that glyceryl acid polymer. All these things are like, it is like, it's a contenders, but still it is like it is in research level, not going to the what I can say. It is like in the system level applications. Okay, but this you can do some kind of like NASA CA program is there. I think Jagadeesh, you know that, no? So I
Yes,
have
sir.
already
Yes, sir. We train
want to do.
students in yes.
It is like you do some different fuel and oxidizer combinations, and which is giving very high specific impulse, something like that. You just try like trial and error. So you can do like you can arrive like different kind of specific impulse at sea level and a very high vacuum level. So it is like if you see the solid propellant, we can get maximum of 260 seconds, whereas in a liquid, cryogenic propellant like liquid oxygen or liquid hydrogen, we can get maximum of 450 seconds at vacuum. So this is the thing. So whatever the fuel you are proposing, hydrogen peroxide, it is like 150 seconds of ISP, something like that, but still we are using for some other applications. Okay, so not really required very high specific impulse applications, something like that. So the thing is like underwater missile or any kind of applications, the rocket propellants means it should contain both fuel as well as oxidizer. Okay, so underwater missiles means we have to use that only, or we can use some water from the sea. We can take it as oxidizer because H2O it contains oxygen. Okay, so then you can use some fuel like as you mentioned, like ADN or methanol kind of applications. So actually ADN, ammonium nitrate or ammonium dinitramide, these are all very, very hygroscopic. Hygroscopic means it absorbs moisture. So the best place for mixing the solid propellant, even for the ammonium perchlorate based propellant also, it is in desert. So in desert only, we don't have any moisture or any kind of disturbances. Only it's a dry place. But nowadays it is even in if you go to Shar Center, that Sriharikota space centers, and they have get the controlled room atmosphere for doing all the solid propellant processing, and it's even it's temperature controlled and moisture controlled. Okay, if there is some moisture, even your room also, if you are having more moisture, means what will happen to your salt or your sugar? So it will absorb some moisture, and it will because it is since we are eating, so it's not a problem. But in terms of energy point of view, if some moistures are absorbed by the ammonium perchlorate or ammonium dinitramide, it's a very it will degrade its overall efficiency. So that's why we required some controlled room atmosphere. So I have used some ammonium dinitramide and ammonium nitrate, but it's very, very hygroscopic in nature. It's very, very difficult. Even after you are completing your propellant processing and curing and during testing, there should also no moisture should be there. So if there is any moisture, it will reduce its performance. Something like that. Okay, so with all above, so you choose any kind of particular solid propellant material. Okay, so then you can go for this thing. So you cover like we can use some solid propellant for initial stages. Even this integral ram rocket, I think you could have studied. What is meant by integral ram rocket? So integral ram rocket means in initial stages, the propulsion is given by the solid propellant or any kind of magnesium-based like paraffin wax or anything, any kind of thing. So we are using it. Then it is the ramjet. It will shifted into ramjet mode and scramjet mode, because ramjet cannot operate less than Mach number 0.7. So we have to assist to take this flight into the Mach number of Mach number 0.7 or 0.8, then only the ramjet will work. So then obviously it can turn into scramjet modes. Okay, so you come up with some diagrams on what you are going to do. So anyhow, you fix some propellant case, then you can choose some trajectory kind of which kind of trajectories you are planning to use, at what speed and what is the altitude. All those things you should specify in the next presentation. Okay.
Yes.
Mujba? Okay.
Yes, sir.
Okay, fine, Mujba. See you. We'll see you in the next class, next meeting. Okay. So, okay, Jagdish. So I have to take lunch. So then
Okay.
after half an hour or 40 minutes, I will come back. Okay. Let's say
Okay.
like now it is 15:30. It's 3:30 now.
Okay.
So I will come at 4:10. Okay.
Yes. Yes.
Okay. Please.
Okay. So there are no celebrity after 4:10. So we were in a present banana. Those are presenting today.
Next will be Aditya Amit.
So,
Yes, sir. Okay, sir.
Aditya, can you come by 4:05 or like when Jaraman
Okay,
said,
sorry, sir.
can you present by 4:10? Like Jaram sir is out for lunch, so we will be back by 4:10.
Okay, sir.
So we can restart the session by 4:10. Is it okay for everyone? Okay with everyone? Or if anyone has time issues, you can present. Okay, some of the things which is going on, going at Vaayusastra currently is there are some 26 to 30 students. They are building their own sugar rockets, and they are doing all the CEA calculations, doing load cell test, like all hands on. And in next week, by next week, they'll be launching, doing a solid like horizontal launch. I'm planning to add some applications like some sensors on the payload section, or even putting a camera which is made out of Arduino module. And, we are going to collect the data using that. So if you guys are in IIT, like in the campus, you can join us. But I'll ask Pvt to update you. Anish Srivatsa, you have a workshop like till what time? What workshop is that? Like, till what time it goes? Anish?
Bro, and some other students have a lab or workshop after 4:30 to 7, I think. 4:30 to 6. Yeah, 4:30 to 7.
So whoever like present can present now. Like Anish, one person can present until like 4:10, I guess, one or two people. Others have to do this like 15 to 20 minutes in between. Like, I thought today is some government holiday or something. Is it? No? Leave out to
Leave it, Kandama.
to our staffs. I thought today is okay. So Anish, you can present if you want to go quickly.
Okay, sir.
Because the input you get from Jaraman sir will be much more helpful. Rotating detonation engines. Start.
Am I audible?
Yes, yes.
Okay, so my topic for research is rotating detonation engines. This is a new type of engines for propulsion of rockets and other aircrafts. So in conventional engines, we use the combustion process goes through the flame propagation is subsonic, so it doesn't cross the speed of sound. So this is preferred because of its controllable nature and to ensure the safety of the aircraft and so that it doesn't explode. But the reaction zone progresses to the medium by the process of diffusion of heat and mass. This generates a lot of entropy. So these engines have a lesser efficiency, and the engines follow an isobaric process. Now, in detonation engines, the engines use a particular composition of fuel and oxidizer such that the flame propagation speed is supersonic. So the flame, the reaction zone progresses as a shock wave, which increases the pressure. And this leads to higher efficiency because the entropy generated is significantly lower than conventional engines. These engines follow an almost isobaric process. So there's a 25% increase in efficiency if we use a rotating detonation engine. So in detonation engines, there are two types of detonation engines: pulse detonation engine and rotating detonation engine. Pulse detonation engine is just a straight tube in which the fuel is injected, and so basically what happens is the fuel accelerates from the intake. The fuel flame accelerates from the intake and it gradually reaches supersonic speeds, and there it reaches through the process of DDT mechanism, uh, deflagration to detonation transition mechanism. So, but this limits the maximum possible frequency in which the pulse detonation engine can be operated, and this limits the maximum possible thrust. So to improve the efficiency, we need rotating detonation engines. In rotating detonation engines, the combustion chamber consists of a concentric cylinders. So the fuel and oxidizer mixture are injected into this combustion chamber, and the first wave is triggered by a pre-detonator. So after the first wave is triggered, it goes around the whole combustion chamber and gradually reaches supersonic speeds. As it reaches supersonic speeds, the pressure inside increases, and this increased pressure expels out of the nozzle, which generates thrust. And as the wave reaches the freshly injected fuel and oxidizer mixture again, it ignites that, it consumes that, and again this feeds the wave, and this cycle keeps repeating. So in this way, it's a self-sustaining cycle. And so this is the diagram of a rotating detonation engine.
So Anish, okay, so the diagram is okay. So what we can do, like how like we can design it. Can you design it using any softwares? We can try 3D printing it, and first try it with like how it like physically how it looks. We can try that like using PLA kind of materials, not like actual propellants or anything. Like,
yes, sir.
Yeah.
Yes, sir. I think we can do that.
First, you can do that. Okay, next, continue.
Yeah. So in future, rotating detonation engines will be used in rocket engines, ramjet engines, turbojet engines, missiles, UAVs, etc. These engines are valuable because of the higher efficiencies, and because the detonation wave itself generates such high pressures, there is no need of extra turbines and compressors. So it saves a lot of weight, and the extra efficiency means lesser fuel needed. So again, we can lift higher payloads.
Like currently, where it is used, these kind of engines?
Sir, it is under development. Only a few countries have demonstrated it successfully, like USA, Russia, and I think I forgot. There was one more country. I think China.
Okay.
Yeah.
So what we can do, maybe we design something like just first to check that how it rotates and all these things. Even maybe water jet can be used to try checking whether it how it works. Let's see.
Yes, sir.
Try designing one and send that. If you are on campus, you can come there. We can try 3D printing it.
Yes, sir. I'm in campus.
Okay, nice. Done.
Yeah.
Thank you, Anish.
Yeah. Thank you.
Is any more slides there? Instability.
No, sir. Done.
Done. Okay, thank you. Come next. So who is rushing for the workshop? Then the next one. Anish. Okay, Aditya, you can present.
Okay, sir, 1 second.
Do we note பண்ணிக்கோ?
Yeah, yes, bro.
Last year present பண்ணா? Who presented last?
Anish.
Anish போட்டு 3D printing.
Yeah.
Aditya. Yes, sir. அதுக்கு முன்னாடி present பண்ண ஸ்டூடெண்ட்ஸ்க்கு we need to buy the some of the solid propellants he mentioned local marketல கிடைக்குதான்னு பார்த்து we can try little small level like maybe
Actually for those materials we need some permission. Nitrate those things are கிடைக்காது.
Okay.
We'll see.
Okay. Who is one more person who wanted to go to like having had a workshop? Who was about to share the screen? Aditya Raja.
Aditya Agarhari.
Okay. Who is not there now? Suchitra. Ashwin Balaji. Ashwin Balaji, if you are here, you can present. Suchitra illaya? Illa. Ashwin.
Vishal, you can also present.
Vishal, are you in a hurry?
No, sir.
Okay, then wait. Like once Jayaraman sir comes.
Okay.
Those who are in a hurry, they can present. We have like 15 minutes, 20 minutes. One more person can present. Ashwin Ashwin, his name is there.
Yeah, yes, sir.
Yeah, you can present that.
Yes.
You have a workshop at 4?
Yes, sir. Can see my screen, right?
Yes.
Yeah, I'll make it quick. So based on for this week's report, I looked around what are the existing things for the search and rescue drones, the SAR drones, which is my topic. So mostly in India, the majority of the drone startups are mainly focusing on photography, surveying, military, agriculture inspections, mostly with some hexacopters or fixed wing. Okay, both have some few advantages. Hexacopters, they can be easily maneuverable, but fixed wings, they have a larger range, like 20 kilometers or something, based on their motor specifications. So far, as I have searched, there is no company which is dedicated to give any search and rescue missions. or they don't provide any search and rescue missions in a swarms way, which I am suggesting. So recently, Chennai-based startup lended their drones to our government for some search and rescue missions in Uttarakhand. That was basically using drones and some camera and imaging sensors to search some people within some caves and in some avalanche. But in any of the startups, they didn't come up with an idea, or they aren't using any swarms kind of technology, which I am which I have took up which I have took up for this intern.
Got it. Got it.
So for the swarms mission, these are the basics, some basic sensors which we'll be definitely using. One is the battery, of course, and some camera, which is the main thing, and a sensor called Finder. I'll tell about Finder next thing. A sonar sensor, which is used to detect some buildings or obstacles, and a Wi-Fi communicator, which is used to communicate between drones. That's my swarm mission, and a GPS receiver. So Finder is a sensor which was developed by NASA and JPL back in 2014 for their some rocketry missions. But later they also found that this sensor can be used in even search and rescue, because this has a very special capability. It can look for people's heartbeat and their breath temperature, even if they're buried 10 feet below their debris. So even if an earthquake or something happens, even if a person is buried 10
yes.
below the debris, then this Finder sensor can help to detect where they are located. So using these type of sensors in a like swarm mission can help to detect survivors instantly while flying and communicate back to the ground station. This is a sensor thing. So the basic framework which I'm trying to use is behavior-based artificial intelligence. There are two approaches in artificial. There are mainly two ways. One is knowledge-based and one is behavior-based. Knowledge-based is like pre-programmed. The method of solving a program is already defined, and the program runs in the same way to solve a problem which the robot encounters. But behavior-based is somewhat different. It gets the data from the sensors and decides what to do at the instant. So while we are flying a SAR mission, a search and rescue mission, based on the environment which the drone is around, it can execute plans or do some changes based on its environment instead of going with knowledge-based systems. So there will be I have taken up 3 type of algorithms for to search an avalanche area. One is a standard method, which I'll be telling later, spiral method, and scatter method. So the first image is a standard method. So with a satellite image, I can just give the four main locations. Example: this gray area, and this gray area, and the drones will just move from this base station to all these three base stations. I mean, to all these 3 gray areas. It is like a direct way. The second is spiral method. So spiraling method is while the swarm of drones reaches a specific way, if it finds some survivors there, with the help of the Finder sensor, if it finds some cluster of survivors, because if an earthquake or something happen, people usually go to collectively go to some spot. People don't scatter and run away, but they collectively go to some spot. So if a drone in the swarm finds some survivors, it starts to spiral them to collect more information, like how many people are there, are they dead, or are they still alive or something. So the second thing is spiral based method, and the third is scatter method. So scatter is completely different. It's mainly like scattering in a very random way, in such a way that it covers most of the exploration area. So okay, this is the last slide. So the basic framework for the behavior based artificial intelligence will be these all things. These all are some kind of different modules. Like this is the launch module, this is our traffic avoiding module, this is climb module, and recharge module, height, form, seek, waypoint, and wander.
So Ashwin, so what I did, So I have collected few videos for you. I sent you in personal chat.
Okay.
So here, so the coding of drones, basic coding of drones. We can try. There are some tutorials which also explains how to make a basic dancing, like say 4 drones are there. You give different positions, it will go there, come back to the same position. So
Okay.
those we can start off with this. Now this is nice. So this will work. It has a huge scope in future as well. Nice. So we can try that. So let me know what are things you need. You can try buying those and try these things.
Okay.
Then you can.
This is like the basic framework, and for all these 3 methods, this frame will slightly change.
And you should, I think, the Python knowledge. You should, you know Python.
Yeah, I know Python.
Okay, super. Then you can use that.
Okay, fine.
And I think
I'll
one
see
of
you
the
use it.
links, yeah, you can watch
Okay.
videos. Let's see. We can try these things.
Okay, so I'll
Super,
come up
thank
with
you.
the implementation of how we do this by next week.
Super. Done. Nice. Okay,
Okay.
thank you. Aditya Agragari, you can present.
Yes, sir. Sir, am I audible?
Yes. We can jump to third slide.
Yes, sir. Sir, in previous presentation, I have already given the need and importance of the rocket fins. Like they provide a stability and give the correct path to rocket and provide a stable flight. So in this presentation, what I can do, like what better things I can do that I have put it. So first of all, we can, sir, I thought to make a design such that we can attach the booster. So first of all, that is needed. What is needed is center of gravity and center of pressure should be at a large distance to each other for a stable flight. So what can we do in that? So to do so is in the nose part, we can make the nose part a bit larger area and attach the booster. Instead of attaching the booster to the tail end, we can attach the booster near nose part. Now the problem is the booster will create a high amount of heat which can destroy the structure of the rocket. So for that we have a material. We can use the material that is tantalum carbide and hafnium carbide, which is able to sustain a temperature of which is stable 400 degrees centigrade.
Okay, is these materials available readily or like what is like have you?
These are sir, like these are alloys. These are man-made, means artificially made. These are not naturally occurred. And sir, using this way, sir, we can make the center of gravity to the upper side of the upper side of the rocket, and so this can so that will create a large distance between center of pressure and center of gravity. Next thing, what can we do is, sir, we can airfoil. The shape of the rocket fins can be made of like shape can be made of airfoiling that. That airfoiling structure provides more lift to rocket at smaller attack of angle of attack. Also, sir, it reduces the drag. And sir, for making the material of the airfoil, that fins, we can use sir, carbon aluminum and titanium alloy. That will reduce the weight of the rocket fin also. And sir, also we can like we can.
Do you think these materials are lighter? They are heavy.
Yes, sir.
I think titanium, the carbon-based materials are, the density is very high. Like,
So
it's
that will
heavy.
that are very strong and lightweighted, right? So these are also used in aircraft and all everything. These alloys are used.
Puvi, you did a basic thing on shape memory alloys, no? Regarding titanium, like nitinol and carbon composites, they are high dense. They are heavy, basically.
Carbons.
Yeah.
So sir, I think like we used to play badminton and all. These things are also carbon. When these are of carbon based, these are so lightweight.
The structure has to be changed. Structure has to be changed in such a way. They are strong, but we need to design it such a way it's lighter.
Yes, sir. So they make it in a shape of airfoil, and which can this has many benefits. Sir, in the airfoil shape of airfoil, that where it is attached, it is of thick portion, and the edge get thinner. Like tail of the airfoil get thinner. So this reduces the moment of inertia also.
Next. So what we can do quickly, so Aditya. So what next slide? What's your next slide? So effective. So you have the idea now. You got the idea. What the next slide?
Sir, we can also use that rocket fins and all get since these are attached in first stage boosters which get separated. We can also make them reuse.
No, I'm just seeing how to implement these ideas practically. Go to next slide. Next.
Sir, by using method of thrust vectoring.
Yeah. Okay, without fins. Okay, next.
Up till there, I wanted to make the rockets with using fins and the.
Okay, Aditya, which design software you are good at?
Like, sir, I'm not experienced in that.
Any software, no, like.
No, sir, not yet.
Then you need to learn some design softwares. Now, convert all these ideas into drawings. Like, did you start learning engineering drawing?
Yes, sir.
Super.
AutoCAD.
So AutoCAD is enough. AutoCAD is enough. Just draw these whatever ideas you are mentioning. No.
Yes, sir.
Let's try designing few fins, and let's start implementing it. Next slide. Go to next slide.
Okay, this much only. Like my idea was to. Like,
I got the idea.
We
can test it. We can test it. But we cannot use these kind of materials at starting. First, let's make the design. Start making the drawings side by side.
Okay, sir.
Yes, thank you.
Thank you, sir.
And Aditya, who has the workshop, who wants to run fast? Suchitra?
Can I go?
Yes, please.
Yes, I'll just share my screen. So is my screen visible?
Loading. Yes, please.
Yes, sir. So so yesterday these were last week these were the ideas that I had told I would search on. So I started with swept back grid fins, and I found out that these were the geometries that were currently in research. So I read a research paper in which these were so there were different cases, different angle of attacks used, and different.
Is this a drawing made by you?
No, sir. I got it, but I'll try this out also. That was my plan, to try these out.
If you design this, we can print it and test it in real time. Okay, next. Continue.
So yes, sir. So these were the different configurations. The down ones are the X configuration and the plus configuration.
Okay.
So swept back, what are the advantages? And yeah, swept. This one is the swept back one with the 22.5-degree angle sweep. So I was reading on how to do what are the advantages and what does it actually do, and I found out these. I just wrote a summary of that. What I understood from the research paper, they had actually used CFD, computational fluid dynamics, to understand it, but we didn't learn much about it. So whatever I understood from that research paper, I've written it as a summary in this presentation. So yeah, so at low and transonic Mach numbers, the X configuration has slightly more control. So it helps us in landing while coming back. It helps us in landing with more accuracy, and there's a slighter drag reduction also, and pitch stability also the X configuration provides. And then yeah, the higher stability, and it gives a lesser axial force value also, the X configuration. And then the swept case also reduces the axial force. These were the advantages that I had found.
I have one thing. So in drones, I can understand this one difference between plus and X configuration. But in rockets, I don't know how far this X and plus. Yeah.
Yes, sir. In this this one, this is the abort motor. So in the plus configuration, it is at 45 degrees to the abort motor.
Okay.
But in the X configuration, it is aft to the abort motor.
Got it. Nice.
So that's what that was what the research paper was talking about. So I was reading on that. So next I was thinking to see different other ideas also, to see if we can implement 2-3 ideas in the same thing, like coarseness of the lattice also into swept back, and there were different grid fins with the peaks also involved in the webs. So compiling different ideas and seeing if they will make into a better model for the fin. So that was my work for the next week. So these all I found in this 1 week. So I'll find some other research paper after that and I'll read on it.
Done? Okay.
Yes, sir.
So you know 3D softwares?
No, sir.
AutoCAD.
So, but I can learn. I can try to learn in this 1 week.
Because we can try this. This is like much more simpler to try.
Okay, sir. So in the next week, I can try learning the design software, and I can try.
You can come up with the design itself. If you pass the design, you can even print it and do some tests.
Okay, sir. Sure.
First, with the general airflow or a water jet, we can try it.
Okay, sir. So I'll stop sharing?
Yes. Yes, sir.
Sir, I'm sorry, sir, I couldn't hear you. My net is a bit
No, it's fine. Yeah, it's fine.
Okay, sir. Thank you, sir.
Next, who is next? Hello. Who is next?
Next, Vishal can present.
Vishal.
Yeah.
Hello.
No, Jayaraman sir is back. Yes.
Yeah. Okay. Go to presentation mode. And...
Yeah. So. Yeah. Good afternoon. So this is Vishal, second year undergrad from mechanical department. So last week, Dr. Jayaraman sir had suggested me to look into the fluid dynamics of a design that I suggested, or the analogies that I had. That is, in last week's presentation, I talked about the evolution of amphibious missiles. So also we saw the state of the art, and the state of the art amphibious missile nearly has a short trip inside water, and majority of its all the technical aspects of it come into play only in the air. So the state of the art is Trident 2, and it uses a submarine, and from water it comes up, and after that the rocket propellants will get into action. So I would like to analyze the coefficient of drag versus the attack angle characteristics of a water mobile amphibious missile near the free surface, and planning a strategy for an efficient surface. So analyzing the CFD part is from a paper that I read, and the water mobile amphibious missile and suggesting a strategy is what I'm going to do. So we saw that the Trident 2 is a intercontinental ballistic missile, and they use solid propellants because mainly because using jet engine technologies inside water, the fuel will flame out, so the flame will go off. So the solid propellants are the only thing that that can work inside water, but they do have the disadvantage, like they have to carry their own oxygen, and the fuel alternatives like hydrogen peroxide, like the previous presenter spoke. So those things will come into play, and these are still in research area. So what I would like to suggest is the mechanism by which the amphibious missiles come to surface and go above the surface, and process requires that the submarine had to be directly under the point on the surface of water through which the missile is going to come. So the existing process is this. So this essentially means that there is no maneuverability of this Trident missiles underwater, and only after the trailing end is above the water surface, engine thrust starts. So this doesn't really mean much control inside the water for the Trident missiles. And by a quick
Vishal, just
calculation, we could see that the
what about the thrust in inside the water? We require more thrust or less thrust when compared to air?
Sir, actually the drag would be more, sir. So just through its momentum, the missile is trying to come out of the water. So what happens is that an explosive flash vaporizes the tank of water into a steam, and then purely due to the pressure it's coming out, there is no engine turning on, there is nothing happening. The cap opens up, and then due to this flash vaporization, the missile barely makes out of the water free surface. So the disadvantages are the disadvantages are the submarine must be directly under the surface portion of the sea, and also there is an explosion happening inside the submarine to give the momentum to the missile. So this is an extremely delicate process, and multiple safety measures have to be made to not make the missile go off underwater in the submarine itself, where the captain is present and so the So it doesn't also provide the maneuverability inside the water. So the objectives for such a design that I'm proposing, a water mobile amphibious missile, is first we should obviously, before finding any engineering solution, we should analyze the physics of it. So we will see, assuming that a missile is going underwater, how can that moving missile can surface the water and go up. So for first analysis part, and second designing a multi-type propulsion system like the previous speaker talked about. Like first we are trying to do solid propellant inside water, and then scramjet and those jet engine technologies above the water. So those things we'll see later. In the fluid dynamics part, and one term I would like to introduce is immersion ratio. Immersion ratio is by the schematic, you could see that the axis of symmetry of the missile, and from the axis of symmetry to the free surface, let's say the normal distance is h, and then the diametric portion, the diameter of the missile is d. So we are going to call this immersion ratio as h by d. So to make sense that when h by d is 0.5, that is half, the missile is just touching the free surface. And that's one thing. So earlier works, and before these papers works were done, not with the shape of a torpedo, but with spheres and so on geometric figures. So what we could see is that as we come closer and closer to the free surface, the properties in the coefficient of drag and other parameters fluctuate to a significant extent comparing to the missile being well below the free surface. That is, we could see that at point the 2.5 immersion ratio, above the 2.5 immersion ratio on the free surface, there will be much fluctuation, and below that, that is beyond that immersion ratio 2.5 depth, that is that is a well-defined parameters and data. So this study, that's a table, and this I would like to focus on this diagram. That is in the x-axis, there is the immersion ratio. That is at 0.5, we start from 0.5 because above which the missile would have come out of water. So 3.5 is well below the free surface. 3 is coming a bit up, 2.5 a bit up, and up, and then at 0.5, the surface of the missile is touching the free surface. And the y-axis is the coefficient of drag. So we could see that as the angle of attack is increasing, the coefficient of drag is changing very much near the free surface. Obviously, assuming that the missile is first going under the water horizontally, it has to change the angle of attack to come out of the water. So as you come near the free surface, changing the angle of attack would result in extremely fluctuating coefficient of drag. So there has to be some plan or strategy to perform such an action. So the plan, I would like to suggest is that, so to give a brief intro, the previous studies indicate that the CD and the radius of the parameters won't change much for a given attack angle at a well depth inside the water. But assuming that the missile would be in a mission inside water with an immersion ratio of 3.5, that is, its h by d is 3.5, and below with the angle of attack is well defined. So during surfacing, obviously it's coming near the free surface. So from the data from this paper, they had done such a work on a torpedo-like shaped geometry. So at an immersion ratio of 3.5, we could increase the angle of attack from 0 to 4. That's because if you see the graph, the thick bottom graph is the angle of attack for 0. So initially the missile is horizontal, no angle of attack, 0 angle of attack, it's just going. So it has to start its initiation to surface. So at that point, at the immersion ratio of 3.5, we could increase 0 to 4 because the first dotted line above the thick line is for the angle of attack of 4 degrees. And you could see that the CD has actually decreased. The coefficient of drag for an angle of attack of 4 has decreased for a 3.5 to 2.52. So this would actually help us to maintain the efficiency of fuel because CD is not increasing so much. It's actually decreasing. In the second step, we are
just one minute. This is from the paper, from the experiment,
no,
or
like the plan is I'm suggesting the data is the paper. Yeah.
Okay, paper you could have mentioned, but why in the immersion ratio or 2 again it is the CD value is slightly increasing than decreasing? Is there any reason for that? They have mentioned in the paper.
No, sir. But I think doing even in CFD software, some fluctuation may happen.
No, it's not from CFD software. No, is it from CFD or it's from experiments?
They have used the CFD software.
Okay, so then they could have mentioned why it is that surge happens in the immersion ratio 2. Is it?
I don't think so. It's not that. So.
But anyhow, it's like immersion ratio. If it is increasing, then it is always CD value should drastically come down. Yes, so. Right. But anyhow, so it's beyond that, it will be almost constant. So that is fine.
Yeah, sir. In the process of surfacing, the immersion ratio is becoming lesser and lesser.
Yeah, can you go to previous slide? Yeah, can you go to previous slide? I have slide. They stated that the immersion ratio decreases, the flow structure changes drastically. What is it actually?
Sir, like the process of surfacing means
ratio,
the immersion ratio decreases.
Let's say if immersion ratio decreases means the flow structure changes drastically.
As in, I will show diagrams on the fluid things in the next slide, sir.
Okay.
So at 2.5, so this is like the plan I'm suggesting to maintain not a significantly increasing CD, so as to prevent the missile from just spinning or going in spirals. So here is the fluid flow CFD software they have done. So as you could see from the last, like the bottom column, it's well below the free surface with a immersion ratio of 2.5. And coming above that is 1.5. Coming above that is 1, and then 0.75. 0.75 and 1.0, you could see that the U by U infinity, that is the U component of velocity by the flow stream velocity, that is in red color, because this portion, the red color, is actually going faster in the direction of the free surface flow. So it's like a jet-like flow is happening as it coming near and near to the free surface. So as you could go below and below the surface, there is there is near symmetry flow structure here at the bottom column, like the bottom row, and at zero angle of attack, there is much symmetry here. But as you go up and up near the free surface, the symmetry is actually reducing. But as you increase the angle of attack near the free surface, the symmetry is increasing. Like as in the asymmetry is increasing as we go near the free surface, but also as you go near the free surface, if you also increase the angle of attack, there is symmetry regain. So this is actually a this is actually going to help us, because we want some kind of predictability in a wake region, even though wake regions are much unstable and unstable. So we would this is a bit of a good news for us. So the asymmetry of the wake structure was increasing as the angle of attack was decreased and the immersion ratio was decreased. Now this is V by free stream velocity, that is the V component by the free stream velocity. So in this, the flow region affected the vortex formation. We know that as in introductory fluid mechanics courses, like when we keep a cylinder passing through the free surface and then the water flows, there will be some Kármán vortex sheet forming behind the along the wake region of the cylinder. So that kind of vortex could form as the missile is just coming out of the water. So what this shows us that the flow region affected the vortex formation with its high magnitudes of downward movement. We saw that I told that there is a jet-like flow as the missile is slowly coming near the free surface. Here, the top row in the second row, h by d 1.0 and h by d 0.7. So that's the red color region, right? So that red color region, there is a jet-like flow. And that jet-like flow is going to help the water to actually come down near the trailing end. So this is helping us to not make the water to separate from the body of the missile. So this is also a good news for us. So we don't want it separating. Separating means even more instability and extreme feedback mechanisms to be included that would much affect the fuel efficiency. So also, and at alpha 12 degrees, that is the angle of attack 12 degrees, early flow separation happens, because it is at 7.5 at 0.75 immersion ratio, it is just touching the water for an angle of attack 12 degrees, and there will be some vortex generation at that case. But as the angle of attack was increased, smaller trapped vortices were observed. But these are still smaller, and this is some good news for us. And here given is the streamline diagrams. So the S is the S and F, the S is the saddle point, and the F is the rotational flow center. So saddle point is where the velocity field has its magnitude as 0, and the F is the focus of the rotational flow, like around which all the velocities would be tangential. So we saw that the velocity along the streamline, velocity cross streamline, and this is the streamline diagram. So as we could see, as the immersion ratio is lowered and lower, the saddle point is coming like towards the trailing end, that is the end of the nozzle. if the torpedo has a fin, the saddle point is coming near and near, and as the saddle point is coming near and near, the trailing the size of the wake regions also reduced. That means there is good amount of knock separation in the flow. So we've reached the presentation. So the first 2 points are what we found, and then I had given a plan for a control of missile for h/d 2.5, and this plan was suggested taking into consideration that the CD doesn't increase much or decrease much with angle of for a given attack angle. So there are this is a research paper, but obviously it has its downsides because we have only considered 4 discrete values of angle of attacks: 0, 4, 8, and 12. So definitely there will be a point. There will be a immersion ratio, and according to that, there will be a angle of attack that we have to make in the mission so as to get the missile outside water. So further research has to be done, and we could do this by designing a prototype and taking it to the fluid mechanics lab and doing it inside the water. So yeah, we have discussed the physics of an important process that had to be done for a proposed water mobile amphibious missile. That is, the missile had to have some control inside water, and then when needed, it has to go up and then hit the target on the surface. So we could see that the engine technologies like turbojet, scramjet, ramjet, they are air breathing. So essentially, in cruise missiles, they are present because cruise missiles, they go for a longer range at a constant, near constant velocity. But then inside water, if you take the jet engine technologies, it would flame out the fuel, and this is not something that we want. So when it comes to torpedoes, they don't use the jet engine technologies. There is a technology called water jet, but it's not taking in the water such a way that a aeroplane is taking in air. So the next step would be to design or bring a schematic of a design that has some multi-stage or multi-type I would call it, because the first process would be maneuverability inside water, and then second would be to go upside in the air. So the first step would involve something of a torpedo's tailing end. Like there are different geometries in torpedoes tailing end, like Atlas, Blackfish, and there are papers on that. So we would first have to figure out the final, that is the first type engine, and then after it comes out of the water, it has to detach that trailing end, and then the rocket propulsion should happen. So this is something that we need to look into, and we have to come up with the trailing end design.
No, Vishal, it is. Can you reproduce this fluid dynamic result with any one of the software?
Yeah, sir. So I'm a second year mechanical engineering. So I have never done any courses on it. I could barely,
Vishal, so we have MOU with the company in Kanna. They can help you out this. So
Because yeah, you can blindly you can follow this, but it's my opinion is like you take a lot of research areas like optimization of this vehicle configuration and using what kind of fuels which will give better performance, all these things, trajectory. So this is actually good actually. So but if you can reproduce these results, this will be a good one. Yeah. Okay, it's my opinion. So they have mentioned only the the immersion ratios and only angle of attack. So you can vary the velocities for different angle of attack, so that is giving because you cannot say like the vehicle will swim only in a particular speed. So it can go with the different range of velocities.
Yes.
So obviously, our angle of attack and these factors will influence that. So So that could be the thing. And the fuel needs, it is like anyhow. So we have different kind of solid propellant fuels, and we can choose any one of that. Okay. So it's something like that. So it is like we have to optimize the design so that we can, as I mentioned, how this dolphin is using some changing its body for different velocity, something like that. So it is some you can try. I think Jagadeesh, you can help him out, like because it is like a low speed flow. So we don't have to go for like very high meshes or like more computation time. Yeah, you can use it. It's very low speed only. So I think since you are from mechanical, so you should use proper terms of like angle of attack and drag coefficient should be like something like that. Okay.
Yeah. Nice.
Okay, Vishal. Done. Nice. So then, who is next?
Yeah. Aditya Raja, Aditya.
Sure, may I call
Next
it?
is Aditya Amit.
Okay.
Shreya, you are in a hurry or something?
Yes, sir, I'll present my screen. So, sir, am I audible, sir?
Yes, yes.
Okay, so last time I prepared the slides for amphibious missile, and I didn't have I didn't have any base to what I should work on. So it was decided that I should work on scramjet engine in the hypersonic missiles. So this is my preparation. So I'll take through the basic part very fast, and then I'll come to my major ideology. So yeah, first I introduce what is a hypersonic, and basically hypersonic is when we exceed Mach number to about more than 5.
You're from aeronautical, no?
And then no, sir, I'm from mechanical engineering.
Okay, so then carry on.
Yes, sir. So then there I have shown some of the, I have written some of the names of the old hypersonic missiles, and then evolution. And then these are some of the recent ones, like this Boeing X-51. So here also they have used scramjet engine, and similarly BrahMos 2 and Shaurya. So yeah, and so there are many engines available. So based on our requirement, we use engine like turbofan, ramjet, scramjet. So I am working on scramjet since hypersonic missiles require scramjet, and for high Mach number exceeding 6, we use scramjet engine only, and this is the level of propulsion they provide. So yeah, so there are certain challenges, like because it is it works at a high operating speed. So the biggest challenge is the aerodynamic drag, and so yeah, and also the heat that is induced due to this drag, due to viscosity. So we need to choose the material smartly so that it should be able to handle the temperature. And also there are structural constraints that because of the vibration, the material should have capacity that it should not lead to some crack or failure. Then also we need a high advanced stability to control this advanced control system to complete this. This was not my research. I want to focus majorly on the engines. So yeah, so this is scramjet engine. So basically this is the one of the version, or we can say the advanced version of the ramjet engine. So in ramjet engine, usually the combustion occurs in subsonic region, but here the combustion occurs in supersonic. So that is why the name supersonic combustion in ramjet engine, abbreviated as scramjet engine. So then I have explained about working of the scramjet engine, and then some basic history about it. How did it come into the existence? And these are the parts of the scramjet engine: converging inlet, combustor, and lavaging nozzle. So basically everything is ram effect here. Due to because of the ram effect, the suction happens, and then it goes to the combustor, and then finally to the diverging nozzle. So the diverging nozzle part is responsible for the thrust which we require. So I have explained the function of the major parts of the scramjet engine. And then again, working principle. So yeah, the advantages here is because like in turbojet engine, we have moving parts, we have compressor and turbine. So whereas in the scramjet engine, there is no moving part. It's simply a inlet body, converging inlet, combustor, and diverging nozzle. There is no turbine or compressor as such. And yeah, so it has less weight, it is easy to manufacture, and most importantly, it can attain speed up to Mach 10 with hydrocarbon, and with hydrogen fuel, it can even attain higher Mach number. And again, it has some disadvantages also. Its cost is high, and also, yeah, the good material, insulation material that we require here should be good because there will be more heat generated. And yeah, it does not operate in atmospheric pressure. So now I'll come to my main part, which I am focusing on. So I first found the problems with the scramjet engine, so that I narrowed down to problems with scramjet engine. So there are many problems, like because this scramjet engine is operating at very high speed, so there's a chance that fuel might not ignite at all, or even if it gets even if it ignites, it can take place outside the combustor region. It means like because the speed is so high that there's a chance that our combustion region may get shifted or some. So we need to take care of this problem. We need to work on this. And also the temperature, as I said, there will be extreme high temperatures. So we need to take care of the material. We need to choose material that should handle it. And yeah, and the biggest problem is in this scramjet engine works only in a supersonic region. Like we purposely want it to work in supersonic region. So to work in supersonic region, we need some initial propeller. Like the missile won't have high speed on its own. To have scramjet engine working, we need some initial Mach number that is attained by other engine sources. Like we can use a rocket booster, or we can use any other engine to attain that Mach number. So till now, I'll call this Mach number as entry level Mach number. So till now, the entry level Mach number is 5 to 6. But what I am studying right now is I'm analyzing how can I reduce this entry level Mach number, because if suppose we use a rocket booster to attain this entry level Mach number 5 to 6, we'll have to have some solid propellants inside, and there will be oxidizer also maybe. So because of it, there will be unnecessary weight, and also for the same weight to attain high speed, we'll require a higher, more complex system. So that is why we should aim to have a low entry level Mach number with same output as compared to this high level Mach number. So yeah, so I am working on reducing the scramjet's starting Mach number. This will have many advantages. One of them is the overall weight will be reduced. Also, payload will be available then. So yeah, so basically there are two fuels which you can use. One is hydrocarbon and other is hydrogen. So hydrogen, as I said in the previous slide, this will have even higher Mach number. And for hydrocarbon, it's about 8 to 10. So I am referring to a research paper by University of Texas. So there it is specifically mentioned, they are analyzing it for about a Mach number about 3.5, but we should try to have it at least around 4 or so. So I have listed some of the methods from which we can reduce this entry Mach number. So the first one is the variable geometry thing. The inlet will have variable geometry by using some actuators. We can use this. We can vary the inlet geometry. At the inlet, there is a conical thing which in the nozzle region, in the entry region. So that structure we can change by using some actuators. But again, this was not very effective since actuators require complex system. And the other option is to use dual combustor ramjet. yeah, here this we can use. What we do is basically because there's a problem of having supersonic combustion efficiently, we can instead use two combustor. The combustor will begin at subsonic region, that is called as subsonic dump combustor, and then it will act as a fuel for the supersonic combustion region. Even this had its disadvantages. I could not find much on this, but I will do it when I come again. So, and yeah, and the third option is to basically modify the design parameters only. Like if we vary the temperature ratio, for example, this is one of the design parameter. There are various things. This is one of the design parameter that if we can vary the ratio of temperature at inlet of the combustor and at the free stream, like the main entry, if we can vary this ratio, if we can control this ratio, we can have a Mach number which can be around 4 or 3.5. So that is what our aim is. Yeah, so that's all. And I have also started working on the fuel required and fuel to air ratio. I haven't concluded it yet, so I have not mentioned it as of now. And yeah, so these are my future plans that I will continue in the next 10 years. So I will continue to analyze the methods by which we can reduce this entry level Mach number. Also, yeah, behavior of the fuel ratios impact. And also, I want to understand how do we design, like how do we decide certain diameter for our requirements. So I found a resource for this also. So I will work on this part in the next 10 years. And finally, if time permits, I will make the model of the jet engine using Clio software. Yes, so that's it from myself.
Yeah. So then entry level Mach number reduction. The thing is like, can you go to previous slide?
Yes. This one.
Yeah. So here, what is happening means essentially, this one.
Yes, sir.
So in the external or compression, here it is there, no? So in this case, here it is like the kinetic energy is converted into pressure energy in the diffuser. Okay. So that means it is like your entry level Mach number should be Mach 5. That is, then only we can call it as a hypersonics. So less than that, we cannot call it as a hypersonics. So your Mach number should be more than 5. Okay, so if you are if you want to decelerate this Mach number 5 to very low Mach number, so your kinetic energy is converted into pressure energy, no? So the obviously your pressure and temperature will be increased.
Yes, sir.
So if you are increasing if you are decreasing so much, because why we are not going for ramjet? Ramjet means the combustion should take place in subsonic region.
Yes, sir.
So you are in which year? Third year or fourth year?
Third year, sir.
You know, so you have studied already this gas dynamics, jet propulsion, everything. So
yes.
In this case, if you are so if you are decelerating the flow from Mach number more than 5 to less than Mach number 1, so it creates so much pressure as well as temperature, because the temperature is the one which decides the overall thrust. What is the temperature difference? The del T. So let's say your inlet temperature to the combustor is 1000 degrees centigrade. I think I have already explained. So because due to combustion, you can have like a temperature of like 2500 degrees centigrade, only the del T of 1500 degrees centigrade. So that del T has to propel the vehicle.
Yes, sir.
So that is very difficult. So that's why we are decelerating the flow, not to subsonic. It's like, let's keep it like Mach number 1.5 or 2 or 2.5, something like that, so that your increase in the static temperature will be reduced. Let's say if it is less than Mach number 1, means you can have the temperature of 900 degrees centigrade, means if you are keeping it as a supersonic flow in combustion chamber, so the increase in temperature could be like 500 or 600 degrees centigrade. So, but okay, so this 500 or 600 degrees centigrade with respect to 2500 degrees centigrade, so your delta is somewhat increased, so that you can have net positive thrust. That is the aim.
Yes, sir.
Okay, so that's why we are going for scramjet engine, and still it is like since it's very, very difficult to stabilize the combustion inside the scramjet. That's the major issues, but still you can work on some different fuel and different the flow, the dimensions like configuration, so that you can somehow optimize it. So I think these are all like a basics you have taken from something, but you should follow some recent journal paper which is published.
Okay, sir.
So they have used some some configurations, so they could have attained some kind of flame stabilization and some sort of pressure loss, because the pressure loss inside the combustion chamber is a very big issue.
Yes, sir.
So that means your total pressure loss P0 is reducing, means your net thrust again it will reduce. So we have to keep the del P0 as minimum as possible, so that we can optimize the total scramjet engine performance.
Yes.
So you have to keep it mind all these factors, so that you take some 1 or 2 journal papers recently published, and we'll see in the next meeting. Okay.
Okay.
Okay. Okay, Aditya.
Yes, thank you, sir.
Yeah.
I'll stop sharing.
Yeah. Okay.
Next is Shreya.
Next will be.
Yes, sir. 1 minute. Good evening, sir. So this week I've been working on the model. Actually, I was given the topic fins, and as mentioned in the last week, I was working on the elliptical fins. So I studied more about it, and I tried to model it in this open rocket software to see the simulations and how the velocity and stability these numbers can be with the model that I create. So I also read that opting 3 fins is efficient, but to align and for other reasons, it is said that having 4 fins is suggestible, so is preferable. So I used 4 fin model here, and I adjusted the length and diameter and all according to the in such a way that I get good stability, and like the CG will be ahead of stays ahead of CP. I have considered all these points, and then I came up with this model. And I also have studied about the general rocket's diameter and length. Since we are working with the basic model, that is something like open rocket, I thought these the diameters and lengths that I have used are okay for us. So here I have kept basic things that are necessary, like rocket and shock cords, and I have used one basic engine. So if we want this apogee to go beyond this value, we can just simply change the motor here with a high power one. Then we can get the desired apogee, and the maximum velocity also changes with that. So yeah, this elliptical fence, as we discussed earlier, for subsonic and generally also it is the aerodynamically best fin. So I worked on this, and I have also read about the materials that we can use. So G10 fiberglass is the material that is widely used in these days for manufacturing of these kind of rockets. So here I put G10 fiberglass while opting while selecting other criteria, selecting some material and length and all the other things. I put component material as G10 fiberglass. So if that manufacturing is easier for us, then I'll go ahead with that, or else I'll change it to PLA or something else. So another thing is I have also read about testing, because once we have the model, we have to maybe test it. I think in the IIT Madras campus itself, we have 3-point bend testing equipment for this kind of test. So in that, once we test it, we get some plot like this, and once it is a good value, then we are set to go. So this is the fiberglass that and this is how they manufacture it. So I think we are only manufacturing it. That is why I didn't study much about the manufacturers. Or else, even though if we are not manufacturing it from the campus, we can order it from India Mart. I saw the availability there also. So I worked on these. So selecting the diameter and working on the actual values took a lot of time. So to get the desired stability, if you see, the stability is also a good value here. And then I am now I'll be making CAD design in this way. So it is given in this research paper, like how to design what are the criteria that we need to select while modeling the rocket and open rocket and the other CAD information related to the CAD software. So in this way, I'll also make the CAD design for my fins, and I'll come up with that by the next week. And I'll also take suggestions from the mentors as to what to do, how
Okay,
to
so then
proceed with
that's
this.
fine, Shreya. So then what is the temperature it can withstand? Do you know what is the flow temperature in the over the fins? Do you have any idea about that?
Here,
From aerodynamic point of view.
Specifically, I haven't studied about the temperature at which it can withstand. I'll just check it out now.
What is the operating temperature of
mention
this kind of materials, and
Yeah.
it should be compatible with the actual flow conditions?
Generally, G10 fiberglass is actually used, sir, widely used. So I think it is okay to choose this material. Also, I'll confirm it and mention that in the next meeting.
But he has
I'll
done it
note
this
that.
time. So then you do some work on that groundwork. So what is the
Yes.
temperature and over the flow over the fins? So if what is the Mach number over that, and based on that you can find out what is the temperature of the flow, so that the fins can withstand that much temperature. And you can use some other materials or some optimization of material configuration for the shape, so that so whatever you are doing, it is good actually. So but we need because if you are producing something, so if you are producing some car or whatever it may be, so first you see the ground reality. So then what is the speed, mileage, all these things there. No? So like that, here also you should target like so this is the actual flow conditions, the temperature and the velocity, all these things.
Yes,
For
here,
that you are making like on fin material and some shapes, so that it could withstand.
Yes, sir. Here in this software itself, we'll get the maximum velocity that it can reach. So that is available here, and I'll work on the temperatures and I'll get that information by next week.
Yeah,
Yeah,
always
just can you click the simulation thing?
Yeah.
What is it? Time versus altitude.
Yes, sir.
Okay, fine.
It's like 400 meters.
I think last week would have presented all these things, but it is always like your presentation should be like a appended one, not like a new one. So based on that previous presentation, so what is your improvement in this 1 or 2 weeks? Something like that you should show.
Okay. Yes, sir. Yeah.
Okay, so fine, Shreya. So then Puvi, who is next?
Shreya.
Thank you, sir.
Yeah, hello, sir. I'll be presenting next. Yeah, hello.
Yeah.
Yes.
So last week I presented about a few ideas in which aerospike nozzle was the one which I went through. Designing the aerospike nozzle as I'll introduce it in the next slides.
Yeah.
So the advantages, like the aerospike nozzle is altitude compensation and it saves fuel, and the expansion ratios are also quite high, like 200:1 and 300:1. So which increases the thrust and specific impulse, and it's better suited for SSTO flights, single stage to orbit. there are few disadvantages of aerospike, like a slip stream effect, which reduces the nozzle performance, as when the air outside the rocket get disturbed, then because the outer boundary of the nozzle is basically the atmosphere, and if it gets disturbed, it might decrease the performance. At higher altitudes, the bell nozzle kind of performs a little bit better, but if we better than the aerospike nozzle. But if we use a truncated aerospike nozzle, then it will reduce the mass and might increase a little bit performance. And the main big disadvantage of not being able to find, like we can't find aerospike nozzle currently in use, is lack of research in this field. And whoever does this will require a lot of upfront cost, as it needs to produce data, test results, and everything on so. So what I will be doing this week, next week, and what I was trying to do this week is contour design based on CFD. So that is basically to generate data and understand the flow effect of flow effect. Study the supersonic flows as it introduces turbulent effects on the exhaust gases, which are quite complicated to study. So I've been reading this paper for a short period of time, design and optimization of aerospace nozzle by Naveen Kumar. He presented this paper on 2017, so it's recently new. It's a relatively new paper, in which he mainly discusses about different types of nozzles, and also discusses about the design altitude and effect of the stream on higher and lower altitudes than the design altitude. So basically, after design altitude means at higher altitudes than the design one, the pressure on the spike is constant, so we don't see any increase in performance. But at the lower altitudes, the wall and the expansion ratio changes according to the atmospheric pressure. So yeah, after that he uses these functions to calculate the contour of the spike, the thrust angle, the Prandtl-Meyer function, and throat area are calculated using these functions. The Prandtl-Meyer function takes the input as exit Mach number, which calculates the thrust angle and the throat area. So in the paper, he mainly discusses about three different types of three different versions of the aerospace nozzle. One is full length nozzle, another one is 40% truncated nozzle, and another one is base bleed nozzle, which is truncated. So in the full length nozzle, the mass is quite high, but it also produces more thrust, as the exhaust is still pushing. Exhaust gets more area to push to the rocket. And in truncated, the mass decreases, but at the same time, the thrust also decreases. So, and in the truncated base model, we get a little bit more thrust. We get a lot more thrust, and the base is also decreased, but at the same time, the mass flow rate increases. These are the few conclusions which he presented in the paper. What I am planning to do next week is to reproduce these results on my own, as the paper only used these three versions, which might not be sufficient to understand the effect of nozzles at different altitudes, as all the results are produced at the design altitudes. I will also be trying to understand the effect of temperature, as in the entire paper he used only a constant temperature fluid, that is at 300 Kelvin. So yeah, that's my take to this week. Next week I'll be using some CFD software like Ansys Fluent to reproduce these results and improve on them.
Aditya, on what basis they have mentioned like 40% truncated bleed configuration could improve 14% of thrust?
Based on the CFD results, they presented these.
Thrust coefficient, or what is it?
What?
Based on the thrust coefficient, or how they are measuring?
Yeah,
the
based on the thrust. Yeah, the thrust decreases. And the thrust decreases and increases, and based on the truncation.
Its total weight also. Okay, so it is based on the length, so it is reduces, so it is 29% reduction. It is. I'm suspicious about the results, so please explain it very well in the next thing, or you can reproduce it by your own by some.
We can try reproducing the results using CFD software, and also we
Yeah,
can,
so then,
if you
because
come up with a model,
29%
you can,
weight reduction is. Yeah, 29% weight reduction means everybody will go for that. So why they are not using it? We should.
Yeah,
Ablative heat transfer issues and erosion and all these things are there, but still, it is like you should like with respect to axis of the nozzle, how the flow parameters are varying, particularly thrust coefficient and pressure, velocity, temperature, all these things you should. Draw separately. Okay, in separate.
We'll try to reproduce the results and we'll present it next week.
okay, even we can 3D print on scaled model of it, the small motion.
Okay. You have already done?
Yes, my
presentation.
Then Puvi, just you can get the model and try to print it. Aditya, are you in campus?
Yes, I'm in campus.
Maybe after your quarantine period, you can come to our office. We will teach you a little bit of Cura and how to print it in the 3D printer. The scaled version of it.
Okay, sir. I'll try to.
Yes.
I'll try to reach you.
3D printing, which material you are using, Jagadeesh?
PLA, sir. PLA. So you will get some idea how it looks and all these things. Metal composites available, and that also it can be done. Next, I'm planning to buy that metal composite printer.
Metal matrix or metal alone?
The metal and PLA, any metal with plastic.
Yeah.
Now a full metal is like cost around 80 lakhs to 1 crore. That will take time. So
So that some GE and some Vibro, they have. So it's like outsourcing company. So but still GE producing by their own, but Vibro is like just purchasing from outside of the country, and they are just selling here. They are like acting as a dealer. Okay.
I'll stop sharing.
Yeah, that's fine. Yeah.
Last presentation, Manashweta.
Yeah.
Yes, sir. I will go ahead. Actually, like I selected multiple topics and I discarded them and again selected.
The voice is broken.
We don't like Instinet isn't working, sir. So
okay.
1 minute. Can you see my screen, sir?
Yes.
Yeah, we are seeing and skipping also. So then, okay. So what is your plan? So what you are going to do in the drones?
Sir, finally I decided to research more on UAV to UAV communication, sir. But actually in the middle I did like research on other stuff as well.
Yeah. So last time you.
Last time I didn't do anything, sir. I did applications of drones and wrote like lists.
Yeah, so then this is also okay, future developments. Okay, so what you are planning to do? So in which area it's like you are planning to write some algorithms, or you are improving the like communication systems, or
I think communication, sir. Like UAV to UAV communication is less focused on.
Okay, so what is the frequency range, and so which should not be interpreted with the government agencies frequency. No, you should know that. No, what is it actually? What is the range you are planning to use? The communication data. What is the frequency range?
Okay, actually, like drones do not actually have a specific frequency range, right, sir? Like it's unlicensed, right? Like there is no spectrum available only for drones.
No, that is also specific. No, so sometimes it is like if you are using like government agencies, they are using some sort of frequency ranges. So if you are using,
I'll search for that. Sir.
Yeah, it is not. They will not allow you to use that. Anyway, that is fine. So then, so what you are planning to? So the communication between the user and the drone is okay. So how do you make the communication between two drones?
Okay, sir. I'll move to that slide. Actually, like I like radar modes also I researched and then I stopped and decided to do that, sir.
Okay.
And then I did micro UAVs and then micro UAV swarms, and finally like communication between drones in swarms, sir.
Okay, so you come up with some idea.
Like I just wanted to focus more on this, sir. Like I actually thought like I wrote some ideas, but they aren't like people actually have them, sir.
Already, okay.
Yes, sir. That's why. Like this one drone, like it can be used to monitor another drone. Like micro UAVs can't carry many sensors, and weight restrictions will be there. And
what is your planning? So you are just deploying one drone. Already some drones are there in that area. Or what is it actually?
For communication, sir.
Yeah.
I think like they use ground station only, sir. Like they definitely use ground. They're researching on this, I think, sir.
Okay, so Manushita.
Like broadcast channels do exist.
Sir,
okay, yes, sir.
Have you done any?
You fix up some idea so that then you research some journal articles, recent journal articles. What is the current status? So in that you can improve upon some configurations or improving some concepts, something like that. So it is like what is it? Co-op channel? What is it actually?
Like I call like between two UAVs, sir. I saw a research paper which can like unlike the broadcast channel, this is like between UAV and UAV.
So what is the purpose?
Okay, that's sir. I have like advantages list also, sir.
Okay.
Like it improves the autonomy of swarms, sir, like UAV swarms.
Avoidance and data transfer and gathering and the benefits in terms of spectral and energy efficiencies. Autonomous flight of UAV swarms. Actually, it's already two drones are there. You are communicating and you are making communication between them.
Yes, sir.
How do you do it?
There are. Wait, sir. I wrote a list for that, sir.
Okay.
These are the ways to like UAV to UAV communications options. We have multiple options, sir.
Okay. Airborne transponders, SATCOM link, Wi-Fi radio link, okay. Long-term evaluation data link, and okay, ultra-high frequency. So then, so these are all the options. So which you are using? You are planning to use?
Like I looked at airborne, like Wi-Fi and LTE. I have been researching. So like the last three are the more viable options
for micro UAVs, I believe.
So what is the range? Let's say if one UAV is there like some 1 kilometer away from another UAV. So which is very up, something like that. So based on the two UAV ranges, okay, something like that. So,
yes, sir. Yes, sir. So Wi-Fi module range is like less than 3 kilometers, sir. 3 kilometers.
okay, so then less than 3 kilometers, it is quite acceptable, I think so.
And UHF, like this is like they're saying it's extremely advantageous, but I haven't researched more, sir.
Okay.
It's like 20 kilometers, sir.
Okay. UAV range itself nowadays, it's the maximum is like 500, so 50 to 100 kilometer only. So based on the fuel which is available, so you cannot fly more than.
And cellular network, I think it's this is also nice. Like cellular network, it's like unlimited. They said, sir. Like
Okay.
I have to fix the topics here. Actually, like I grew quite indecisive and I researched multiple things at once.
That is fine. So these are all the options. So you should select any one of these concept and you can work on it.
Yes. Should I like I'll research all three and see which one is the best, sir?
It's up to you. So if you have
Okay,
time, you
sir.
can do all these things. So,
Yes, sir.
so
Like,
we are not from electronics background, but still it is. We are like always looking for it.
Yeah.
So,
Oh, actually, I selected communication because I'm from EE, sir. So
yeah.
more suited to me. I
Yeah,
thought.
yeah.
Like I don't have any experience though. Sir. Like nothing.
It is fine. So no problem. So you have to use your idea so that you can improve it. The operating range is allowing BLOS control and external cellular coverage and reduced backhaul demands. What is it actually, that point?
Backhaul, sir.
Yeah.
I think it's like related to ground station, sir. Like I do not know the exact definition. I researched it like a while back.
It is like feedback signals data.
Yes, sir.
Manushrita, you are in campus now?
Yes, sir.
Oh, super. Okay, so what we do, there is one technique which I was reading about this US Air Force they are using. When they fly a Air Force airplane, so there's one more UAV or a unmanned airplane which will be flying from this actual aircraft which is flown by pilot. He also able to control the one which is flying side by side, which is like unmanned. So this is one of the technologies which I read recently and they are using it. And to use that, first we should do some basic hands-on works. Have you tried anything hands-on data transfer related things, Manushrita?
No, sir.
So what you can do, you can check with Puvi and you can come anytime Monday to Friday or Monday to Saturday to office, or even Sunday will be there. So there is something called LoRa module we used to teach train students in data transfer.
Okay.
So we will, that LoRa module itself is good enough to transfer 25 kilometers without any, if there are no barriers or no disturbances, it can transfer 25 kilometer data, but very small kilobytes of data. So that that training you can get it. Okay, once you do that, we ourselves inside our office have drones, like a small drones, which can fly say 100 meters or 50 meters. We can fix this LoRa module under this drone and try to transfer the data from the drone to ground station, your laptop. That we try first. Once you successfully do that, we can have two drones with one LoRa module acts as the transmitter, one LoRa acts as the receiver. We can side by side try to fly both of it and try to transfer the data. Okay. So whenever you are free, just check with Puvi and come to office, start learning this. Hello. Can you able to hear me? Hello, Manushrita?
1 minute back, your voice was.
Okay, I got a call, so I disconnected. So wait, okay, so
It's
I'm
against-
getting calls. So so you can come to office anytime and learn these basics. Also, we can teach you some of the PCB design related to transmitter, receiver, and all these things. So you can take it to next level. Done?
Yes, sir. Yes, sir.
Okay.
Yeah. Okay, Manasrita. So then.
Thank you.
Yeah.
Okay, thank you, sir.
Yeah. Thanks. Okay, so Jagadeesh. So
Yes, sir. Thank you, sir. Thank you so much. So
then the last week they have presented some more than 12 or something like that, no? So this week only some 6 or 7, something like that.
புவி எத்தனை பேர் present பண்ணாங்க? So I think நிறைய பேருக்கு ஏதோ workshop இருக்குன்னு they have kept on putting messages. நான் சொல்லிட்டேன் என்ன நடந்தாலும் we have to do. Mentor meet is important. So I think.
Well, because I kept it this today's meeting because of Sivakumar. I thought you will bring some 12 or something like that.
Space food
biotech students, so that because of him. Otherwise, we could have done it some weekdays only.
Space food students, அவங்களுக்கு
no
exam இருக்கு சொன்னாங்க.
Students, you can fix up some time so that.
Yes, sir. Yes.
So then we can have it. Okay.
Yes. Thanks.
Okay, Jagadeesh. So then.
Thank you, sir. So
anything else?
Then I'll fix up space food on the meeting and I'll coordinate with you and sir.
Yeah, maybe in the evening also, because for us it's not a problem. So here we are like 2.5 hours.
Okay. So in 7 o'clock we are going live. Space food, the students now they're just presenting some history and all these things.
Okay.
Next week full exam முடிச்சிட்டு full fledged ஆரம்பிச்சிடும். By 6th week we are planning to cook some foods and test and testing facilities எல்லாம் கண்டுபிடிக்க சொல்லியிருக்கேன். So பார்க்கலாம் எப்படி போகுதுன்னு. ஒரு full fledged curriculum develop பண்றதுதான் plan for space foods.
Okay. I think he will help you out now. No issues. Yeah.
Thank you.
Okay, Jagadeesh. See you.
Thank you, sir.
Thanks, guys. So see you. Bye.